All right, here are a few example problems that are a little more challenging, or maybe we haven't thought about them as much anyway. This is comparing atomic radius versus ionic radius. So atomic radius versus ionic radius. This can be a little bit challenging. Let's talk about it. First thing we need to know is when an atom loses electrons, it forms a positive ion. When an atom loses electrons, a positive ion or a cation is formed. Okay. One way I remember this, it's a cation because it's positive, right? Because cats have paws. I don't know. It's just one way of remembering it. Anyways, when an atom loses electrons, a positive ion, a cation, is formed. So when a sodium atom loses one electron, a sodium ion is formed. Sodium atom loses one electron, a sodium ion is formed. So we want to compare the radii of a sodium atom to a sodium ion. Let's explain this, okay? So we're going to write the electron configuration for sodium and then the sodium plus ion. So looking at Na, that's in the third energy level. So that's going to be 3s1. It ends in 3s1, right? And right. 1s2, 2s2, 2p6, 3s1. Now, if we were to write the sodium ion electron configuration, we're just going to get rid of that 3s1. So it'll be 1s2, 2s2, 2p6, and we lost the 3s1 electrons. So you notice that we have actually one less energy level here. So if we have one less energy level, then automatically it's going to be, that electron's going to be closer to the nucleus. And it gets sucked in even farther because sodium has more protons in the middle of it than whatever the noble gas before sodium is, which is neon. So it's got more protons than neon, so that those valence electrons are pulled in even farther. So when we get a positive ion, it's always going to be smaller than the neutral atom. Here's our conclusion. A cation is smaller than the original atom. And the reason is because the cation has fewer energy levels than the original atom. As you see here, we dropped down to the previous valence shell because we lost all the valence electrons, gave those away so it would be like a noble gas. So we have fewer energy levels, that makes it smaller. When an atom gains electrons, it's different. When an atom gains electrons, a negative ion is formed. We already know this, I think. And a negative ion is called an anion. When an oxygen atom, let's use this as an example, an oxygen atom gains 2 electrons, an oxide ion is formed. We want to compare the radii of an oxygen atom and an oxide ion. So we're going to write our electron configurations for both. Oxygen has a electron configuration ending in 2p4. It's right here, so that's going to be 2p4. One s2, 2s2, 2p4. And then if I wanted to write the oxide ion, it's got a -2 charge. That means I've got more electrons than I did. So it would be 1s2, 2s2, 2p6, Now, I didn't change the number of energy levels. We've got the same number of energy levels now. We also have the same number of protons. So the way that we explain this is a little bit more tricky. A negative ion is a little harder to explain than a positive ion. Let's talk about it. An anion is larger than its original atom. So that's the opposite. The positive ion, the cation, is smaller than the original atom. An anion is larger than its original atom. Let's explain why. Because even though an anion has the same number of energy levels, or we could say shells, and it has the same number of protons, an anion has more electrons than its original atom and greater, this is a really key term, electron repulsion. What that means is we've got electrons that are close to each other, and remember, electrons have like charges, and like charges repel. So if you've got electrons in the same energy level, we got more electrons with no additional protons, so they're not being sucked in closer. We didn't actually go up in energy level, it's just more electrons in the same energy level. Well, if you get more electrons, they're going to tend to spread out. And if they spread out, then our radius gets bigger. That electron-electron repulsion is what we use to explain negative ions. That's really the only time, as of right now, that we're going to be using that explanation. Electron-electron repulsion is the reason that negative ions are larger than the original atom. Have a greater ionic radius. So ionic radius is not as straightforward as some of the other trends. If it's a positive ion, the ionic radius is smaller than the atomic radius. If it's a negative ion, then the ionic radius is larger than the atomic radius. And these are the explanations of why. You do need to know how to do that, how to explain that. Isoelectronic atoms and ions. Isoelectronic means it's got the same number of electrons. So it's just a fancy word for saying we've got the same number of electrons. Let's compare some of these. We want to compare the radii of an oxide ion, a neon atom, and a sodium ion. We're going to write the electron configurations for oxide, neon, and sodium. So oxide is oxygen with 2 extra electrons. We actually just wrote it up here. This is the oxide ions electron configuration, so I'm just going to rewrite it. 1s2, 2s2, 2p6. Okay, that's oxide. Now I'm going to write neon. Okay, neon's over here. It's 2p6, ending in 2p6. 1s2, 2s2, 2p6. Oh, wait, that's the same thing. 1s2, 2s2, 2p6. Okay, now we want to go on to write Na+. See where Na is. So Na is up here, but Na plus would be losing 1 electron. So it wouldn't end in 3s1, it would end in whatever's right before 3s1. So if I lost this electron, if I lost that, I would go back up to the same place as neon, which is 2p6. So sodium plus ion, Na plus ion, would be 1s2, 2s2, 2p6. The same electron configuration for each of them. So what we need to do for atoms and ions with the same number of electrons, the species with the most protons has the smallest radius. Because even though all the species have the same number of electrons, the species with the greatest number of protons will attract the electrons more strongly. Remember, we're increasing that positive charge. Opposites attract. We've got a stronger attraction to the nucleus. And that explains isoelectronic, or if you got the same number of electrons in different atoms and ions.